Alright, this video is going to be a review of rational functions. So first we'll start off with a definition of what a rational function is, and it is the quotient of two polynomial functions. So quotient just means division in math. And so these rational functions are the functions that you see that look like fractions. So the notation for a rational function is going to be r of x, so r for rational, is p of x divided by q of x. So it's polynomial functions, those are like x to the fifth plus 5x to the fourth, something like that, or you might even see them in factored form, but it's polynomials. And this is where q of x does not equal 0, and we just put that in there because you can't divide by 0, and so we want to make sure that our function on the bottom does not make it so the whole fraction is undefined. So the first thing that's going to be important in our review is to make sure that we remember how to simplify rational expressions. So simplifying rational expressions. And an expression is just something that it's not an equation, there's no equal sign. So a rational expression, for example, could be something like 2x squared plus 11x plus 5 divided by x squared minus 25. So here we're going to go ahead and simplify the rational expression. And when we have something written like this, typically the best way to simplify it is to do some of that division, because we have something divided by something else. And to figure out what pieces we could divide out, we're going to go ahead and factor, because factoring is actually a form of seeing what two things have multiplied together. So factoring itself is kind of a form of division. It's like saying if I want to factor 15, I want to see what numbers multiply to be 15. So if I want to factor this polynomial on top and on bottom, I want to see what factors would multiply to be that polynomial expression. So I know that the top is going to be 2x multiplied by x. That's how we were able to get that 2x squared piece right there. And I know that these two numbers over here have to multiply to be 5. So it could be 1 and 5 or 5 and 1. And I'm going to go ahead and put 1 and 5. So 2x squared plus 10x plus 1x plus 5. So we have 2x squared plus 10x plus 1x plus 5, and that works for the top. And then on the bottom, I can see that when I factor it, that's the difference of squares. So x plus 5, x minus 5. Now at this point, I can continue simplifying because I see that I have multiplying by x plus 5 and dividing by x plus 5, and those two operations cancel each other out. X plus 5 over x plus 5 is the same thing as 1. So I'm just going to get rid of those. So this expression simplified would be 2x plus 1 over x minus 5. So when we simplify expressions, we will often factor. Here's the next example. We are going to simplify 3 over 2x plus x over 5 over x squared. And this is called a complex fraction. So here, when you find something that's a complex fraction, the first thing that I like to do, and there's a lot of tricks to this, so this is just, in my opinion, what students prefer from all my teaching experience. What I think is easiest to do is to look at the common denominator for each of the fractions that are within your overall rational expression. So I have 2x and I have x squared. So I know that my common denominator is going to need a 2 because I can see a 2 right here. And this one is x and that one is x squared, so I know I'm going to need the higher degree, so I'm going to need an x squared in there. So you're going to take that common denominator, and we're going to take that rational expression that we had, that complex fraction, and we are going to multiply that fraction by 1. So that means I'm going to multiply it by a fraction where the top and the bottom are the same. And the fraction that I'm going to multiply it by is going to be that common denominator over itself. So what I'm doing here is I'm taking something, I'm multiplying it by 1. It's just a well-chosen 1. And when I multiply it, I'm going to change what it looks like, but I'm not going to change what it equals because I'm just multiplying it by 1. So I'm taking this, I'm multiplying the top together, I'm multiplying the bottom together. So when I do 3 over 2x multiplied by 2x squared, I can see that the 2's will cancel out, and I can see that this 1x will cancel out with 1x right here. And I've got the plus, and I have x being multiplied by 2x squared. And then on the bottom, I have the 5 over x squared, and that is being multiplied by 2x squared. And here I can see that the x squared on the bottom and the x squared right there should cancel out. So the next thing that I have here is I can go ahead and simplify. I've got 3 times x on the top. Over here I have an x being multiplied by 2x squared. So that would be 2x to the third. And then on the bottom I have 5 times 2, which is 10. And so that right there would be my simplified rational expression. And at this point, now that we have taken this from being a complex rational expression to just being a not complex one, it's not a complex fraction anymore. At this point, if you could factor anything out and cancel, you would. But I know that the 10 is not going to simplify with the 3 and the 2, so I'm going to go ahead and leave it looking like that. All right, another thing we would like to be able to do with rational expressions is we would like to analyze them. And in this case, we're going to talk about rational functions. So all I'm doing if I'm going to look at a rational function instead of a rational expression is I'm just going to put y equals in front, or f of x equals in front. So we're going to analyze rational functions. And things that we're going to do when we analyze, we're going to look for the domain and the range. We're going to look at asymptotes. And we're going to look at holes. Those are things that are very specific to rational functions that we want to have command of and be able to find easily. So first, we're going to go ahead and for the instructions, I'm just going to say analyze. I'm just going to ask you to find each of these things. So first thing, if you want to look at finding the domain of a rational function by hand, we just have to recall that domain is the allowed x values. It's the x values for which the function is defined. And so anything in the denominator of this rational expression that equals 0, so I'm going to take this denominator, I'm going to make it equal 0. Anything that makes this equation true, that makes the bottom of this fraction equal 0, is going to be excluded from the domain. So that's going to help me figure out what my domain is. So here I have a quadratic to solve, and to do that I'm going to have to factor it. So I have a greatest common factor here of x, and I'll go ahead and take that out. And then x squared, if I take out an x, I just have the x left over, and negative 4x. If I take out the x, I have a negative 4 left over. And so if I were to solve this, if x equals 0, and this one, that would make the whole equation equal 0. In this one, if x equals 4, the whole equation would equal 0. And so since my domain occurs where the denominator does not equal 0, then this tells me what values I can't have. So I can have all of the x values except for 0 and except for 4. So I'm going to go ahead, I'm going to draw this on a number line because I think it helps students sometimes to visualize it. So 0 is not allowed, 4 is not allowed, but everything else is allowed. So that means from negative infinity up to 0 is okay, from 0 to 4 is okay, And from 4 to infinity is okay, as long as I don't include those specific values. So our domain is from negative infinity to 0, from 0 to 4, and from 4 to infinity. All right, next, we're going to leave a space for range here, but we're not going to look at it quite yet. So go ahead and just leave a few lines. Next, we're going to go ahead and look at the asymptotes in the wholes. All right, so asymptotes and wholes. Asymptotes are those lines that a graph approaches and might cross, but is going to continue to get closer and closer and closer to. So here, for us to be able to find the asymptotes and the wholes, we're looking at x values that cannot be used, so it's going to have to do over here with part of our limited domain values, but it's a little bit more complicated than that. So for us typically to find asymptotes and wholes of a rational function, we want to look at the factored form of the function. So 2x squared minus 2x minus 24 over x squared minus 4x, that's what we started with. So now I'm going to go ahead and look at the factored form of it. And on the top, I can see that I have a greatest common factor of 2, so I'll go ahead and take that out. And that leaves me with x squared minus x minus 12. So on the top, I have that GCF of 2, and then I'm looking for two numbers that are going to multiply to negative 12, but add to negative 1. And the two numbers that would multiply to negative 12, but add to negative 1 would be negative 4, so I have x minus 4, and positive 3. So they multiply to negative 12, add to negative 1. And then we already factored the denominator, so I'm going to go ahead and write that factor in here. All right, so now at this point, I know that something happens at x equals 0, and I know that something happens at x equals 4 because those were the two numbers that were excluded from our domain, and I want to make sure I know which is which. So first, I can see that these two factors right here cancel out, and so that means that that must be the whole. So if there's the whole right there, then that means that x equals 0 is something that's left over but is still excluded from the domain, and that means it's the vertical asymptote. So we have a vertical asymptote at x equals 4. Now at the whole, we know that the x value is 4, but we are actually still able to find the y value if we'd like. So for us to find the y value, we're just going to take our leftovers here from what you get after you cancel out those factors. I'm going to say I have 2 times x plus 3 divided by x, and I'm going to take the 4 that I have for x and plug it in. So that gives me 2 times 4 plus 3 divided by 4. So 2 times 7 is 14. 14 divided by 4. So that means my y value here is 14 divided by 4, which is the same as 7 over 2. So here we know that our whole occurs at the point 4, 7 over 2. All right. Next, we want to look at our horizontal asymptote or slant asymptote. And if you guys recall, you look at the degree of the numerator and denominator. So we're going to start off, I'm going to go ahead and put a heading here, like a subheading. So horizontal asymptote or slant, that's an L. And there are three situations. So the degree of the numerator could be less than the degree of the denominator. And if that is the case, then there's a horizontal asymptote at y equals 0. The degree of the numerator could equal exactly the degree of the denominator. And if that is the case, then the horizontal asymptote is at, and I'm going to say it's the quotient of the leading coefficients. So here, it's the coefficient of the highest degree of the top. So I'm writing coefficient of the degree of the numerator, and then coefficient of the degree of the denominator. And we'll look at that in a second because that is the situation we have here. And then the last case is when the degree of the numerator is greater than the degree of the denominator. And in this case, we know that we have no horizontal asymptote. There would not be one. All right, so here is horizontal asymptotes. On the next one, we're going to say the degree of the numerator is greater than the degree of the denominator by exactly 1. Not by 2, not by 3, not by 4, by exactly 1. So if that is the case, then you're going to have a slant asymptote. Slant asymptote. Okay. So what we're going to do is we're going to look back at our rational function. I'm going to go ahead and write it out again. And you're only looking at the term that is what gave you the degree. And the term is that leading coefficient, or that the highest exponent is what tells you your degree. So we're going to look at these two. I've got 2x squared over 1x squared. And so since my degree is the same, the degree of the numerator is the same as the degree of the denominator, then that means that my horizontal asymptote is at y equals, and it's the coefficient of the two leading terms, I guess. So 2 for this one, 1 for that one. That means my horizontal asymptote is 2 over 1, or in this case, we could just say that's 2. All right, now don't forget about range. We still have to go back and do the range. But what we're going to do is we're going to go ahead and draw a little sketch of this situation so that you guys can see what's going on here. So I know that I had a vertical asymptote at 0. I know that I have a horizontal asymptote at y equals 2. And I know that I have a hole at the point, what was it, 4, 1, 2, 3, 4, and then 3.5. 4, 3.5. So I've got a hole right there. Okay, and now we didn't find it, but if you look at the factored form, so if we go all the way back up here and look at this factored form, the numbers on the bottom tell us domain values that we're going to exclude, and whatever factors you have left over on the top, those tell you what your x-intercepts are. So I can see that I'm going to have an x-intercept at -3. So I'll go ahead and draw that. Now if you did not recall that, that's okay. You would have been able to solve it on your calculator. So I'm going to go ahead and type this in on my calculator. I have 2x squared minus 2x minus 24 divided by x squared minus 4x. And I'm going to go ahead and set my window back to normal here. There we go. And then I'm going to go ahead and just draw a little sketch. So this graph makes sense for us because of the way asymptotes work. I know that this curve is going to follow this horizontal asymptote. It's going to look like that. And now this picture is where we can get our range. So if I look at this, I'm going to go from down to up. So I can see my arrow goes down, so that's -infinity. And then as I go up, I can see we're including all these values. So for the range, I feel pretty good about saying from -infinity up to 2. So -infinity up to 2. And that took care of this curve. Now on this curve, I have 2 as the lower bound, and then I come to this hole, and that hole is at 7/2, so I definitely want to include that. So I'm going to say from 2 to 7/2. And then after 7/2, I can see the graph just continues to increase. So 7/2 to infinity. So there is my range right there.